everybody, and welcome to TLC, the Tom and Lonnie Chat. I'm Dr. Tom Kerpus over at Georgia Tech, and we've got quite a discussion today for you in additive manufacturing and really where it's going and so forth with some of the latest and greatest technology. And so we'll be introducing our guest speaker in a little bit, but let's start to bring on the TLC team now. Lonnie has moved from Oak Ridge National Labs over to Sandia National Laboratory, and so he's sort of taken out a little bit. But we thought, well, we should just keep our podcast rolling. So we brought in one of our favorite guest commentators, Cyber Kyle, and Cyber Kyle is now here at Georgia Tech. Welcome, Kyle.
Hello, great to talk with you again. How are you doing?
I am doing well. Still trying to wean myself off of the slide rule in BlackBerry, but we're moving forward there. So I heard a lot of comments on that one from a couple of episodes ago, but that's good stuff. Anyways, welcome. Good to have you on board here at Georgia Tech, and good to have you substituting in for Lonnie. I appreciate it.
Great to be here today.
All right, and let's bring Stephen on board.
What's up, everybody?
Hey, Stephen. It must be sort of Beard Day or something like that. That's like No Shave November here.
Yeah, ever since the pandemic, I took a shavecation, and I'm not coming back.
Shavecation. Well, all right. Now I've got a new term that I've got to, that's sort of I like that one. Anyways, we'll leave it at that. So how you been, Stephen?
Been well. Been really well. How are you guys?
Doing really well. Doing really well. Keeping busy in the hell bit. Yeah, just very excited about this. We've already been rolling for almost 2 minutes. We need to get our guest speaker on. Stephen, did you want to do the introduction? So you made the contact for us and so forth. I'm very excited about it.
Yeah, I'll make the introduction. So our guest today, I'm really excited about because she is a big hero of mine. Her name is Melanie Lange. And before I even mention her company, I will say this. I feel bad because I've kind of been talking behind her back about the pronunciation of her name, of her company's name, because everybody reads the name and they're like, oh, FormAlloy. But every time I've said FormAlloy in her presence, she's been polite enough to not correct me, but I've heard her enunciate it as FormAlloy. So Melanie, come on in, and how about let's set the record straight. What is the proper pronunciation?
So the proper pronunciation is FormAlloy because that's what we're doing. But it rolls off the tongue, FormAlloy. So, we kind of answer to anything. So you can pronounce it however you want, Stephen.
Gotcha. Thank you.
Well, welcome, Melanie. And we were chatting actually just before the show kicked off. I'm very excited about the technology and so forth. And so what we'd love to do is just hear a little bit about, what's new and exciting, from FormAlloy. Yeah, did I get it right? Yeah, I did. Okay, good. From FormAlloy. But what are your differences? How we can move this forward, and what kinds of impacts we might see in some of the shops. So I'm going to just turn it over to you to kind of spin us up on everything.
All right, awesome. Well, thanks so much for having me. I love talking about technology. I'm actually an aerospace engineer by training and background, and spent most of my career in the aerospace and defense industry, and brought this technology to market in 2016 because I saw a big gap in the ability to produce metal components and get them where they were needed, when they were needed. And it's been an amazing journey ever since. So at FormAlloy Technologies, Inc., which is the full official name of the company, just to make it more of a tongue twister for you, we design and manufacture directed energy deposition systems. And I'll tell you a little bit about what that is. You can also probably refer to it as DED. So you may have heard of DED and wondered what that is. It is kind of an interesting name because directed energy, some people think of different things, but directed energy deposition is an additive manufacturing technology in which an energy source combined with a feedstock will build up a part layer by layer. And how our particular system works is we have powder as a feedstock. So we're typically blowing powder, creating a melt pool with a laser, and then essentially injecting that powder into that melt pool to build things up. We also have a new capability that I'll talk about where we can use wire as a feedstock as well. And there's certainly some unique applications for doing that. And of course, the other benefit of this directed energy deposition technology is it's not necessarily just for additive applications where you want a big, build a big rocket nozzle component that you hear about, probably if you follow additive manufacturing and some of the interesting use cases. Because you're putting the material where you need it, you can use this technology for more traditional repair applications, and also what we call enhancement applications, where you might be using a different material and applying it to either an existing part or an inexpensive substrate to give that particular part, even a higher performance and functionality. So it's a very exciting technology because you can use it in a variety of ways. And I know for, people that work in machine shops or work with a lot of different machines, it's nice to have sort of multi-tool type of machines that can do more than one specific thing. We do sometimes find that making the business case and justification for this new technology, sometimes the repair application is kind of the low-hanging fruit there. Because if you have a part that's only worn in a certain area, or even if you have an expensive part that has been mismachined, you can add a small amount of material back to that part and then get back to your baseline to then, go remachine it. So it's an exciting technology. I see a lot of growth for this technology going forward. If you follow additive manufacturing, there's probably other technologies that you've heard more about than DED, and those would be, powder bed and binder jetting technologies, which I would argue are two of the most widely adopted technologies in the metal additive manufacturing space. And just like all technologies, there's limits. And I think some of the limitations of the binder jetting and powder bed technologies are addressed with DED. And what I mean by that is because we're putting the material where we need it, you can scale this type of technology more so than you typically can with a powder bed, which requires a large bed of powder. On the binder jetting side, you're going to get typically much better material properties, somewhere between a casting and a forging with DED. So you're still going to get that full quality, fully dense type of component that you would expect with traditional manufacturing.
And I'm just curious, as we're sort of getting there, because one of the things I want to ask you is, okay, there are some other DED systems out there, and so I'd be sort of curious as to, what some of the advantages you have with your DED. But before we go there, one of the things that I saw, I think it was a paper out there that I read. I was going to use my coffee cup here, but I don't want to dump the coffee on me. But basically, where if you're using something like powder bed, you're right. So I've got this big powder. I've got to build this thing up, and imagine this whole thing that I printed, but I've got a box of powder around it, and powder's not cheap, and so forth to sort of deal with. But if I were to say, look, I've got a tube that I've machined, right, and so I've machined this out, and I just want to add the handle, I could print the handle onto the base material. I don't have to start by printing the whole tube, if you will, right?
Exactly. And sometimes those are some of the best applications is when you can build the substrate into the part. Yeah. And that becomes very cost effective if it's, something that's very easily readily available, like a tube, or some other type of bar stock available in a certain size or material. And you're just adding material to that and creating something new with it.
Right. Yeah.
I'm glad you asked about that kind of radial part. I have an interesting multi-material part here. This one's really interesting because you can actually see maybe the difference in the color. So the inside of this is actually a copper alloy. You can kind of see it coming out the bottom there. This is a GR Cop alloy, which is a copper chromium niobium alloy. And then the other alloy on here is Inconel 625. So, this can be made different ways. In this case, we wanted to complete this in a single step. So we actually are varying the material within each layer. So that's something that is very unique to us at FormAlloy. We do a lot with multi-material and functionally graded material. We have some specialty hardware and software to help do that. So in this case, we're actually changing within a layer. We're changing between the copper and the Inconel to achieve this kind of geometry. Oops.
Yeah, no, it's sort of hard with the camera going left and right. Yeah, I think that's very cool. And what I heard there was sort of functionally graded, and I really like that because and again, I put my little professor pointy hat on there, right? You have two materials, and if you put them down on top of each other, they're both very hot. When at the interface, then when they cool, they will shrink at different rates, right? And so then you get cracking and popping and all sorts of bad things. But if you could basically sort of blend the materials from 100% Inconel to 100% copper, but blend them, now you don't have this break. And so this to me is amazing. And you're doing it in the same layer. Is that right? So you're not, usually the functionally graded sort of happens layer by layer, but you're doing the same layer.
Yeah, exactly. So you can do it either way. There's some parts, most parts you can decide how you want them built. In some cases, it might make sense to build up in copper in the Z direction and then rotate it on its side and do some type of radial gradient. In this case, because of this particular geometry, we actually had to be able to switch it, interlayer. But that just gives you more design freedom and flexibility as you really look to future applications. And, how do we make things last longer from a sustainability standpoint and perform more so we can continue to do more, go further, and reach new heights.
Yeah.
And I don't want to understate how cool that capability is. From some DED machines, that is a really impressive part to just hold and show. So what is what are some other things that really set your system apart?
Well, a lot of what we are able to do, like you said, for directed energy deposition and placing the material where we want it, we're still getting excellent surface finish. And still the high build speed. And a lot of that has to do with our in situ monitoring and control. So we have eyes and ears on exactly what's happening in that machine and in that melt pool. And we can identify the optimal process parameters very quickly by using some of those sensors in closed loop mode. And then when we're building follow-on components, we can basically have our parameters already set and then just run the same parameters over and over again, which doesn't mean that you have fixed laser power or fixed powder flow rates, because there's little nuances that happen as you change powders or as you change geometry or go from a thin wall to a thick wall, or even as you are in a different position in your Z height and you have different thermal properties happening because now you're dealing with a larger mass of metal versus a smaller mass of metal. And so I think it is important to know that there's variations in the process, and you have to be able to account for those in order to get, something like this which is multi-material, still excellent surface finish, very precise in terms of the geometric accuracy. You have to be able to account for those, small nuances.
So it's really interesting when you bring that up about all these nuances of additive manufacturing. We've got some fantastic machinists and just incredible design engineers. What would you say to them about adopting additive manufacturing technologies and learning those as they were trying to work with a system such as yours?
Yeah, I think a couple things. One is our machines are designed like a machine tool. So some systems are designed as an additive manufacturing system, and someone who is used to running a machine tool is not going to be familiar with the interface or even how the machine works, and it might take them more time to get comfortable with it, or it's really intended for a material scientist or a PhD to run the machine. Our machines were designed by a machine tool designer to run and operate and have the repeatability of any standard machine tool. So typically machinists are happy when they see our machine and they recognize the G code and they recognize the interface, and we can speak in terms of machine tool and what's important in terms of when you're dealing with a machine tool. So I think that's one thing. Is I think it's important as the industry matures to have a shift from operators of machines who are, PhDs, like I mentioned, or material scientists who are running these and identifying parameters, to being able to utilize the workforce we have right now and grow that workforce that is going to be more focused on, CNC machine operation. So that's one thing. In terms of getting them motivated and excited to use it, I would just say to think of some of the big challenges that they have and how they might use additive manufacturing to solve that. For example, if they are working with Inconel, I don't know many machinists who are super excited about working with Inconel. So if you can use additive manufacturing to create a part that requires much less machining than it would if you were hogging out of a large block, those are motivators and can have good cost benefit as well. If you can make something that's, near net shape and take away a lot less. So that's one use case. And then the other, of course, would be, hey, do you ever make mistakes in your machining? Do you ever take off a little bit too much material, drill a hole in the wrong place? If the answer is yes, you could also start using additive manufacturing for that, particularly DED, where you are adding material back into your mistake and then remachining it again.
Right. Yeah. And actually, there's a great paper, and I know Stephen and Kyle know which one I'm talking about. That was published not too long ago, but on additive, where they basically had I think it was a stainless steel base, and then it used to be an entire solid part out of Inconel that you'd machine away, and it would just take forever, and it was costly, and because Inconel is not cheap. And they just said, well, actually, we just need an Inconel on certain surfaces, and so they machined this nice stainless steel tube down, added the Inconel to it, and then just did a little bit of finishing on the Inconel surface, and it was perfect. And we've also seen some really nice stuff on turbine blades, where you wear it away, and so you say, okay, yeah, I want to repair it. So I mean, a little different than I've machined away, but now you machine it down, you add it on, you blend it, machine it all together. But the stuff you put on the tip is a little bit harder material, so now it doesn't wear as much. So your refurb part, right, is your refurbished part is better than your original part, which is kind of cool. So really,
that's a great use case for multi-material. And now I'm seeing more applications where people are becoming more comfortable with that multi-material approach. It can be challenging because additive manufacturing is a new process in a lot of ways. So, people want to shy away from it, or the qualification requirements to adopt a new process is just too much to take on. But I am seeing hope there. And that's another thing I want to mention is that's unique about what we do in our machines. I mentioned that we can see a lot of things that are going on in the machine and make predictions and basically direct the machine to identify the correct set of parameters. But what we're also doing is we're collecting all that data and we're making that data available to the user in two different formats. One is in raw data format that the PhDs will love. It's time-stamped parsable data. And there's another format that is more digestible for people like me and machine operators and project managers, which is a PDF report which summarizes everything that happened in the build. So that way you can compare build to build. You can see if there's any anomalies in your build. And essentially, in the future, we hope to use that as a digital build certification. So I think unprecedented access to data is another thing that we're known for here at FormAlloy. And I know I showed you before we started the recording, I have a t-shirt that says DED-Head on it. So I'll just show that again because it's so awesome. And we have another t-shirt that says, show me your data. I think it's been a little bit challenging to adopt some of these new technologies, because if you can't share the information of what's going on in your machine and it's more of a black box, I do think that's where these, huge requirements come in for making, thousands and thousands of tensile bars and, spending millions of dollars just on testing to be able to adopt the technology before you even start developing your specific application. And I think some of that is derived from there's just been a lack of access to data. Right. And that's what we're trying to change. We're trying to give as much insight as we can on the process so people can build that trust in early and often, and then have that as a kind of a receipt to say, hey, we know this part is good. And we know these parts are consistent. Yeah. And that's something that's, I think, a little bit of a gap right now in the industry in general.
But and I am excited about that. And sometimes I know on the show we've talked about the podcast. We talked about the digital passport. I mean, to me, it's like, look, you're building this thing up layer by layer and so forth. Clearly, you've got some insight in terms of what's happening in there, and so now you've got you're tracking everything, and yes, this thing was made right, so I ship your your airfoil off to to the Air Force, and they know that this turbine blade is good. I really like it in terms of that in terms of that discussion. I'm curious. So sort of all this stuff going on. How do you program? I heard G code and so forth, but I think when we look at some of these, even a high end, even a low end CNC, typically we're gonna go off and we're gonna use some of these CAD CAM package and so forth. How does all that come together? Is it pretty easy to put all that together?
Yeah, I think if you're doing simple designs, it's very straightforward, and it can be done, very quickly. If you're doing very complex geometry parts, it's not an easy problem. But there are tools and there is a workflow to do that. So we are typically starting with a CAD model, or you can start with a scan of a part if you don't have a CAD model available. In fact, the duct that is behind me, that you can kind of see, that large curved duct, that was actually built off of scan data, and there was no CAD model available. So we did build it off of that. But once you have a 3D model in your hands, then you would go through a slicing process, and there's different slicers. We use different tool packages depending on the type of part that we're slicing. But we do kind of also have a standard that we recommend that's based on Mastercam, since that's sort of an industry standard for a lot of machine shops and people that work with machine tools. They typically already have a Mastercam license, so we offer a plugin for Mastercam to do the slicing, and it's a pretty good tool in terms of covers a very wide range of what you can do, from simple shapes. I mean, this part here was sliced using that, and it is somewhat complex in features. I have some other complex geometries behind me, and it is possible. It can take a little skill sometimes to come up with the solution and run it through a simulation, but the tools are getting better and starting to catch up with the capabilities of the technology. Once you have the part sliced, then you run it through a post, and essentially that post outputs G code for our machine that it can understand and has some of the unique features that our machine has. Yeah,
I was going to say not too much different than what you might do, post to a, let's say, a 3-axis, or even when you're talking about complexity. I mean, I think we all know 5-axis programming is pretty complex and so forth. So it's the same thing. And then the other thing that you sort of bring you bring to bear is access to the data. I mean, one can't pick up the paper, or I guess now it's a tablet, no more paper. But you can't look at this stuff without hearing about ChatGPT. That's exactly, all this AI and so forth. And I think all the data are going to go in there, and they're going to help you. They're going to help you. They're going to take care of making a better part, moving it along faster, and so forth. And so, to me, the access to the data is going to also be key. So, looks like everything is kind of falling in place. They really get the DED and so. But by the way, do you actually, does that shirt say? Do you say DED-Head, or do you actually say DED-Head?
Well, for the purpose of the tie-dye shirt, we say DED-Head, but but usually, DED-Head or DED-Head. You can see there's some hashtags on LinkedIn that we've had some fun with some of our colleagues in the space too. So, if you guys want a T-shirt, send me an email, and we'll make all of you DED-Heads.
I already got one. I will say, I'll brag a little bit. I already got mine.
That's right. You do.
I'll happily take another one. But to further emphasize Tom's point with the data, without going as far as ChatGPT, which is great, and it's right around the corner, and it's a matter of time before somebody does it.
I was using the buzzword, Steven.
Sure, that's fine. But if you look at, if somebody was to, make a startup company to make a new CNC lathe today, nobody's adopting a CNC lathe if they're going to hide the data that's coming off of it.
Yeah.
Because we're talking about Industry 4.0, and it's a matter of time before we're talking about Industry 5.0. And when part of Industry 4.0 is getting all of these devices and machines integrated and talking to each other, so you need to know that data. And a company that hides the data and how they format their data and what the data coming off their machine means is shooting themselves in the foot today. And it's also to Melanie's point, it's a bit of an advertisement. See, you don't need to be a PhD to run this machine. It's just a CNC machine But it's think of it, instead of thinking of it as like additive manufacturing as opposed to subtractive, think of it as a different type of cutting tool. Except it's not cutting. There's feeds and speeds, and you've got different data parameters, and subsequently you have different overrides to tweak with as the operator is making a part. It's really cool.
Yeah.
Steve, I always felt like Melanie laid a trap, told us about the trap by saying, "Oh, you'll really like that we have open data," and we still fell right into it when she said we like the open data. I mean, it's awesome to see a company that's being so forward and saying we give you access to not only the raw data but also an easy to read PDF report. That's neat.
Right. And it's like the whole defense of some companies use of, well, we hide the data to, for the security of your IP. And it's like, dude, it's not like 1990 anymore. Like that's not how we protect it. We're not hot gluing USB ports anymore. If you're concerned about that and you don't have an IT department for your machine shop, you need to catch up. That's on you.
I feel like I know we're getting close on time here, but I'm obligated to ask. So how do you see this cybersecurity as we're moving forward? There's so much interest in protecting machines. Where do you guys see that going?
I mean, I think, cybersecurity is obviously a key, issue, concern, and definitely something that should be on everyone's mind. If you have a, small business to large scale business. I also think that it's important for the machines to be able to function and run in the case that there is a cyber event. So I think it is important for machines to be able to sort of be, sequestered off and not need access to the cloud or online access to be able to run. And that's what we've done with our machines as well. So you can have you could put our machine in a machine shop that doesn't even have internet access, and it will run just the same. The data will just stay local to the controller until you pull it off with, whatever media you might put it on, like a USB drive. But it does not require, access to the cloud. The data is not being sent, anywhere unless you direct it to do so. So I think that is obviously, it's not a very technologically advanced answer, but I think it is important that we can maintain some basic functionality in the event there is some type of cyber event, because even with all the great cyber technology that we have, and Kyle, you know a lot more about the subject than I do, if something happens, it can still take time to restore our systems, and you don't want to be in a situation where you lose your ability to do any type of manufacturing.
No, I completely agree. And sometimes you don't need all of that technology. The simplest solutions are indeed the most effective, right?
Unplug it.
I think you're spot on by saying, how do you make sure it works 100% of the time?
Right. I think that's perfect. And so, I tell you what, I'm going to give Melanie the last word, but I did want to just spin everybody up, sort of coming up. So great. We've got FormAlloy, this one, and then next month, look forward. We're going to talk a little bit about some kind of cool EDM type of capabilities. We'll go visit the guys down at the shop here at Georgia Tech, see what's going on. Then in August, so pushing out in August, Microsoft in your shop. I think we all walk through these big shops and factories and so forth, and on all the heavy equipment, you see the Windows screensaver. So what's going on behind there and so forth, and how do we engage? And then we'll and then when we get to the September time frame, I know it's kind of looking out. I won't even tell you about our holiday special yet, but we got a holiday special planned for you, so stay tuned. But September, we're going to kind of do a little bit of a recap of IMTS, so the best of that, so you can see Stephen and Lonnie and myself out there, on the stage having a good time, just kind of reminding you. And of course, no IMTS this year, but in 2 years, 2024, hopefully we'll see FormAlloy and so forth out there in the additive areas and so forth. But so number one, I want to thank everybody. Cyber Carl, thanks very much for helping out in place of Lonnie. Stephen, of course, always good to see you. And Melanie,
likewise.
Thank you so much. I want to give you the last word before we sign off, and over to you. And by the way, these guys will tell you I don't usually give the last word to people, but this is great. I'm turning over to you.
Well, I appreciate the honor. And what I would like to say is, with directed energy deposition, it's just another tool in the toolbox. If you are looking across different technologies, as you should be, you have to find what's best for your application. And just know that DED is a multi-tool. It can be used to repair, it can be used to enhance, it can be used to build parts, but it is just another tool in the toolbox. It's not, DED is not going to replace, a lot of jobs. It's not going to take the place of traditional manufacturing in any way. It's there as another tool in the toolbox, and we're going to do awesome things with it. And we hope more of you do as well.
Respect.
I love it. So this is awesome. And again, I know we're some time away from IMTS in 2024. But man, I'm looking forward to see what you guys have cooking over there. But also just go visit the website and see the process and so forth, because it's very cool. I mean, who doesn't like melting metal, right? I mean, it's awesome. So, all right. Hey, Melanie, once again, thank you so much for joining us. And, we really look forward to seeing great things out of FormAlloy. All right. Stay safe, everybody.
Thank you. Bye-bye.